Hi everyone, this is Dr. Ravindranath Reddy working as Assistant Professor in MLR Institute of Technology, Hyderabad. So today we are going to discuss the Fourier series which is in numerical methods and integral transform. In this video, we are going to discuss what is a Euler's formula and overview of a Fourier series and how to find out the Fourier series expansion for the function f of x in the interval 0, 2 pi. So now Euler's formula. So we are going to take a standard formula to find out the Fourier series for f of x in the interval c less than or equal to x less than or equal to c plus 2 pi. This is the general interval we have taken. So that Fourier series is given by, so f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos nx plus b n sin nx. This is the Fourier series formula we will use. And here we are having some coefficients a naught, a n and b n. So in order to find out the values of a naught, a n and b n, we are having a standard formulas. So a naught is given by 1 by pi integral c to c plus 2 pi. This is the interval we are taking. So this is initial value and this is the final value in that interval. So we have to take that values as the limits of this integration c to c plus 2 pi and f of x dx. And a n value, this next coefficient is a n. So a n is defined by this standard formula, that is 1 by pi integral c to c plus 2 pi f of x into cos nx dx. And the next last one is b n. So that coefficient b n is defined by 1 by pi the integral c to c plus 2 pi f of x into sin nx dx. So these coefficients a naught, a n and b n, these coefficients we can call it as a Euler's formula or Euler's coefficients. So this is the standard formula we will use to find out the Fourier series expansion, and in the Fourier series expansion we are having some coefficients a naught, a n and b n. By using these standard formulas we are going to find out this a naught, a n and b n values. So this a naught, a n and b n we can call it as a Euler's formula or Euler's coefficient here. So now we will go for the overview of a Fourier series. So first we will take the Fourier series here and we are going to find out the Fourier series expansion for the function and the fixed interval. So we are taking a fixed interval here, fixed interval, so in terms of pi, and we are having another arbitrary interval, so which is represented in terms of small l. So in the fixed interval we are going to take the interval 0, 2 pi and the length of this interval is 2 pi, and the next one is minus pi, pi, and the length of this interval is also equal to 2 pi, and the next last one is 0, pi. So the length of this interval is pi. So in the fixed interval in terms of pi we are having three intervals 0, 2 pi, minus pi, pi and 0, pi. So the first two intervals we are having the length equal length, that is 2 pi, and in the last one 0, pi we are having the length of this interval is pi. So whereas if you come to the next this interval minus pi, pi, so we are going to study how to find out the Fourier series expansion for even function and how to find out the Fourier series expansion for odd function, and the final one is neither even nor odd, neither even nor odd. So these are the, so whenever the function is even function in the interval minus pi, pi, we are going to find out the Fourier series expansion, and similarly whenever we are having f of x as an odd function, so in the interval minus pi, pi, so in this also we are going to find out this Fourier series for the odd function, even though there are some functions which are neither even nor odd. So this type of functions also we are going to discuss how to find out the Fourier series expansion in the interval minus pi, pi. And here when you come to the interval 0 comma pi, and this interval is also, we are having two types of intervals, this for half range sine and cosine series, and sine and cosine series. So these are the two types of Fourier series we are going to discuss in the interval 0 comma pi. So this is about the fixed points which are in terms of pi. So when you go to these arbitrary intervals, so we are having arbitrary intervals 0 comma 2l, and the next one is minus l comma l, and the next one is 0 comma l. Okay, so L is nothing but any constant value. You can take L is equal to 1, or L is equal to 2, or L is equal to 3, or L is equal to 4. You can take any value for L, and in that we are going to find out the Fourier series for the given function. So whereas when you come to the interval minus L comma L, so here also we are going to study how to find out the Fourier series expansion for even function and odd function, and the next one is neither even nor odd, neither even nor odd. Okay, so here the same as this previous one, so we are going to discuss half range Fourier sine series and Fourier cosine series. Okay, so these are the concepts we are going to discuss in the Fourier series here. So now, so first we will go for this interval 0 comma 2 pi, and in this interval we will see how to find out the Fourier series for the given function now. Okay, now we are taking the interval 0 comma 2 pi, and for the function f of x we are going to find out the Fourier series. So the Fourier series is given as f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos nx plus b n sin nx. This is the standard formula you are going to use to find out the Fourier series expansion. Now in this interval, particularly in this interval, so 0 comma 2 pi, we are going to find out the Euler's coefficients, that is a naught, a n and b n, that are defined by a naught is equal to 1 by pi integral 0 to 2 pi. In the general interval we have taken c less than or equal to x less than or equal to c plus 2 pi. Now here in this general interval I have taken x is c equal to 0. So if you substitute c is equal to 0, then we can get an interval 0 comma 2 pi here. So by using this, by substituting c is equal to 0, so then you will get a naught is equal to 1 by pi. So integral 0 to 2 pi f of x dx, and a n is equal to 1 by pi integral 0 to 2 pi f of x into cos nx dx, b n is equal to 1 by pi integral 0 to pi f of x into sin nx dx. So these are the three standard formulas we are going to use to find out a naught, a n, b n in the interval 0 comma 2 pi. Now let us take one example and we will see how to find out this Fourier series for the given problem. So here we are having a function f of x is equal to x square. For this function we are going to find out the Fourier series in the interval 0 comma 2 pi. So that interval 0 comma 2 pi is also represented with 0 less than x less than 2 pi. So in this interval, for this function f of x is equal to x square, we will see how to find out the Fourier series expansion now. So already we know the standard form of Fourier series expansion. So take that standard form here. So f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos nx plus b n sin nx. So this is the standard formula to find out the Fourier series expansion here. So let us consider that one as equation 1. Now here the task is we have to find out the coefficients values, a naught value, a n value and b n value here. So now we will see, we have the standard formula to find out the a naught in the interval 0 comma 2 pi. Use that formula. a naught is equal to 1 by pi integral 0 to 2 pi f of x into dx. Now we know the value of f of x, substitute that f of x is equal to x square here. So in that I have taken this. Now f of x is equal to x square. Now this is the formula to find out a naught. So I have substituted that f of x as x square here. Now this is of the form integral x square dx. We know the integral of x square, that integral of x square is given by x cube by 3. Now in this value you substitute the upper limit and lower limit here. So if you substitute that upper limit and lower limit here, so that is 1 by pi. So take that 1 by 3 outside since it is a constant. Now substitute that upper limit. In place of x, substitute x is equal to upper limit, that is 2 pi. So 2 pi whole cube minus lower limit is 0. So 0 cube is nothing but 0. So this can be written as 1 by 3 pi and 2 pi whole cube. This can be written as 8 pi cube. So 1 pi gets cancelled here, you will get pi square. So the remaining one is a naught is equal to 8 pi squared by 3. So this is the way how we can find out the value of a naught by using this standard formula. So now we will go for the next coefficient, that is an. So that an is given by 1 by pi integral 0 to 2 pi f of x into cos nx dx. Now substitute that f of x value, f of x is equal to x square here. So then you will get integral 0 to 2 pi x square cos nx dx. So once if you observe this function which is inside the integral, we are having a product of two functions. One is x square which is an algebraic function, and the next function is cos nx which is an trigonometric function. So whenever we are having a product of two functions inside the integration, so to evaluate this integral we have to go for the integration by parts. So we have to consider one function as u and one function as v. So since it is an algebraic function, we will consider this as u, and since it is a trigonometric function, we will consider as v. So this is identified by taking the help of the word isolate. Isolate. So I stands for inverse functions, L stands for logarithmic functions, A stands for logarithmic functions, and T stands for trigonometric functions, and E stands for exponential function. So here we are having algebraic function and trigonometric function. Out of these two functions, the first algebraic function comes first in this word, and then the trigonometric function comes. So since algebraic function is coming first compared to this trigonometric function in the word, so we will consider that function, algebraic function, as u, and that remaining function as v. So this integral of uv formula. So now integral of uv is given by, so we have a shortcut formula, that is u into integral of v, that is represented with, so we can take that value as v1 minus u cube minus, and in the second step, in the second term, you take the derivative of u, and once again you apply the integral of this v1, that is it becomes v2. Here this is v1 and plus, so alternatively you have to keep plus 1 minus here, and now go for the second derivative of u, and then go for the another time apply the integration for v2, so we will get v3. So v1 is nothing but integral of v, and v2 is nothing but integral of v1, and v3 is equal to integral of v2. Okay, and so on. We have to continue this until we get the derivative of that u is equal to 0. Okay, now by using this standard formula, we will see how to find out the integral of this x square and cos nx dx. So now here we have taken u. So here we have considered that u as x square, so you keep that x square as it is, and v1 is nothing but integral of v is cos nx, integral of cos we can take it as sin nx by n, minus, so here we are having minus, next term is u dash, that is derivative of u, derivative of u is nothing but x square, derivative of x square is 2x, so I have taken 2x here, and now here we are having v2, so v2 is nothing but integral of v1, So integral, this is the value of v1. So once again you apply the integral for this one. Integral of sine, we can take it as minus cos nx, and take this derivative of this nx and keep in the denominator. So already here we are having 1n. So if you apply the integration one second time, you will get the denominator as n square plus next u double dash. So first time if you apply the derivative of u, here we got 2x. So once again you find out the derivative of 2x, that you will get that value is equal to 2, and this is the v2 value, and once again you apply the derivative integral for this v2, you will get that value is equal to minus sin nx by n cube. So by using this integration by parts, by using this standard formula, we can find out that integral of x square cos nx is equal to this value. Now one by one you substitute the upper limit and lower limit here. So we have substituted the upper limit. So after simplifying this, we got this is the resultant value. Now in this you substitute the upper limit 2 pi first and minus lower limit here. So once if you substitute the upper limit 2 pi here, so here we will get sin 2 pi. That sin 2 pi, we can consider that value is equal to 0. 0 into anything equal to 0. We can take it as 0 now. Now here take x is equal to 2 pi. 2 pi into 2 you will get 4 pi, and cos n into 2 pi you will get cos 2n pi by n square, minus here also we are having a trigonometric function sine. So you will get, if you substitute x 2 pi here, you will get sin 2 pi. Sin 2 pi is nothing but 0. Okay, this is the value after substituting the upper limit 2 pi. Now minus, substitute the lower limit here, x is equal to 0. So if you substitute x is equal to 0, you will get 0 square, 0, 0 into anything equal to 0, and here 2 into 0, 0, 0 into anything equal to 0, and here if you substitute x is equal to 0, you will get sin 0. Sin 0 is nothing but 0. So when we substitute lower limit x is equal to 0 in all the terms becomes 0 here. Now simplify this. So you will get sin 2n pi, we can consider sin 2n pi is equal to 1. So finally you will get 1 by pi into 4 pi. So sin 2n pi is equal to 1 by n square. So this pi and this pi gets cancelled. Finally you will get 4 by n square. So 4 by n square is the value of an. So this is the way how we can find out the value of an here. Now finally you are going to get that bn value here. So bn, this is the standard formula to find out the bn value in the interval 0 comma 2 pi. Now here also you substitute the value of f of x. So you will get x square into sin nx. So here also you apply the same integral of uv formula. You consider this as u and you consider this as v, and follow the same procedure here. u into v1 minus u dash into v2 plus u double dash into v3 minus and so on. So this is integration by parts. So applying the integration by using the concept of by parts. Okay, follow the same procedure, you will get that value u into, that is x square into v1, that is the integral of this sin nx. So you will get this value minus derivative of u, that is derivative of x square is 2x, and integral of v1, if you apply the integration here for v1, once again you will get this minus sin x by n square plus u double dash, if you apply this 2 times derivative for x square, you will get that constant value 2, and the derivative of integral of this term, you will get this value here. Now simplify this, you will get minus x square cos nx by n plus minus into minus, it becomes plus 2x into sin nx by n square plus 2 into cos nx by n cube. Now we are ready to substitute the upper limit and lower limit in these values. So substitute these values, 2 pi, x is equal to 2 pi. So 2 pi whole square, you will get 4 pi square cos 2n pi, and since here you will get sin 2n pi, so sin 2n pi is equal to 0, so we can substitute 0 here, and here 2 into cos 2n pi. This is the value after substituting the upper limit minus, now substitute the lower limit here, x is equal to 0, x squared 0 square, 0 into anything equal to 0, and here also we are having x, substitute x is equal to 0, 0 into anything equal to, you will get 0 here, and finally you will get, if you substitute x is equal to 0 here, cos 0 is 1, 1 into 2, 2 by n cube. This is the value you will get after substituting the lower limit here. So finally this is the value you will get. So after substituting this, you will get Bn is equal to minus 4 pi by n. So this is the value of Bn. Okay, now we got A0 value, An value and Bn value. Now after finding this A0, An and Bn, we are going to substitute that values in the equation 1. So our equation 1 is nothing but our Fourier series which I have taken in the beginning. So that Fourier series is given as f of x is equal to A0 by 2 plus summation n is equal to 1 to infinity An cos nx plus Bn into sin nx. Now in this we are going to substitute the value of A0, value of An and value of Bn. So our A0 value, whatever the value we got that A0, so we have substituted that value and divided with 2, this is 2, and plus summation An, we got that An is equal to 4 by n square. So we have substituted in place of An, we have substituted that value 4 by n square and minus this 4 pi by n. This is the value of Bn. Now if you want, we can expand this summation here in both terms by taking n is equal to 1, n equal to 2, n equal to 3 and so on. We can expand this summation in both terms here. So since 4 is a constant, so I have taken that 4 outside, and now you take n is equal to 1 here and substitute n is equal to 1. So 1 by 1 square, that is 1, 1 into cos 1 into x, that is cos x. So you will get that by taking n is equal to 1, you will get the first term as cos x. Now you take n is equal to 2, since it is a summation you keep positive sign, and take n is equal to 2 here, you will get 1 by 2 square into cos 2x plus, now take the next value of n in order to get the next term. So next go for n is equal to 3. So by like this, by substituting, by taking the different values of n, you will get the terms here, infinite number of terms, and similarly follow the same procedure here, you will get this. So once if you observe this total expansion, so this total expansion we are having involving two trigonometric functions sine and cos, then this entire series we can call it as a Fourier series expansion for the given function x square. So this is the way how we can find out the Fourier series for the given function f of x is equal to x square in the interval 0, 2 pi. Similarly, we can take any function, either it may be a continuous function or discontinuous function. We can, by using the same procedure, we can find out the Fourier series expansion for the given functions. So in this session we have discussed how to find out the Fourier series expansion for the given function in the interval 0, 2 pi. So when you come to the next video, we are going to discuss how to find out the Fourier series expansion in the interval minus pi, pi. Thank you all.